Welcome to the this lecture on this course on 3G and 4G wireless communications. Let me start with a brief recap of what we did in the previous lecture. In the previous lecture, we completed our analysis of wireless channel characterization, and we began comparing the performance of a wireless communication system with that of a wireline communication system or with that of a wired communication system. And we said the most important technique or the most important characteristic used to compare the performance of these two systems is the bit error rate characteristic, what is denoted as BER, which is simply if I transmit a stream of bits, on an average what is the probability that the bits are detected in error. So, we said a wireline communication system can be represented as y equals x plus n. Since there is no multipath interference like a wireless communication system, the coefficient is 1. So, whatever is input is received at the output y in the presence of additive white Gaussian noise. We said the noise is of variance sigma n square, which is also the noise power. We said the signal is of power p, hence the signal to noise ratio is p over sigma n square, all right. And then we also derived the expression for the bit error rate of such a communication system. We said the bit error rate is given as the q function of p over sigma n square, which is also q of square root of SNR. Since p over sigma n square is also SNR, the bit error rate of a wired communication system is q of square root of p over sigma n square, which is q of square root of SNR. We also did an example in which we computed at 10 dB what is the probability of bit error of a wire line or a wired communication system. We said 10 dB SNR is equal to SNR of 10, all right, and hence the bit error rate is q of square root of 10. We said there is no closed form expression for this, but this can be evaluated using tables, and the value is 7.82 into 10 power minus 4. We also looked at a plot of the bit error rate versus SNR, and at around 10 dB the bit error rate is, we said, is 7.82 into 10 power minus 4, right. Now, let me continue with that discussion. Let me give you one more example, and then we will proceed on to the bit error rate analysis of a wireless channel. So, let me start with one more example. Another example of performance of a wired communication system. So, this example we want to compute. So, the problem is compute the SNR dB, the SNR in dB required for a probability of bit error, that is bit error rate, equal to 10 power minus 6. So, what is the SNR required to achieve a bit error rate of 10 to the power of minus 6 in this wired communication system? And we can solve this problem similarly as using the approach that we followed previously, which is if the bit error rate is 10 power minus 6, the bit error rate is given as a function of SNR as q of square root of SNR, all right, which means the SNR, the square root of SNR required equals q inverse of 10 power minus 6, which means if I square both sides, the SNR required is simply q inverse of 10 power minus 6 square, that is q inverse of 10 power minus 6 square. Now, again there is no closed form expression to compute this. So, we have to rely on tables. The value of this turns out to be SNR q inverse of 10 power minus 6 is 4.7534. Hence, the SNR is the square of 4.7534 is 22.595, and the SNR in dB is nothing but 10 log 10 of 22.595, which is SNR in dB equals 10 log 10 times 22.595, and this value is 13.6 dB. So, let me summarize what we did. We wanted to compute the SNR in dB required for a probability of bit error rate of 10 power minus 6. We said that SNR in dB is given as 13.6 dB. So, the SNR dB is 13.6 dB for bit error rate equals 10 power minus 6, and it is important to remember that this is for a wired communication channel, or a communication channel in which there is a wire between a transmitter and the receiver. This is for a wired communication channel. Again, let me go back to the PDF plot and show you how, where the point it corresponds to the plot. This point is 10 power minus 6 bit error rate, and that if I compute the SNR corresponding to that plot, that is 13.6 dB. All right. So, the SNR corresponding to 10 power minus 6 bit error rate is 13.6 dB. All right. So, that essentially gives you two examples, and with that we complete our analysis of the bit error rate of a wired or wireline communication system. All right. So, now let us proceed on to derive the bit error rate of a wireless communication system. So, that for the same SNR we can compare the performance of the wired and the wireless communication system and see how each of the systems performs in terms of bit error rate at a given SNR. All right. So, let me start with, what am I going to start with? I am going to start with bit error rate analysis of a wireless communication I am going to start with the bit error rate analysis of a wireless communication system. All right. And we said previously that a wireless communication system model can be represented as follows, that is y equals h x plus n. We said x is the transmitted symbol, n is the noise at the receiver. In addition, there is a fading coefficient that results from the multipath propagation wireless environment, or the multipath interference at the receiver arising from the multipath components present in the wireless communication channel. So, the difference between the wire line and the wireless communication channel essentially is the presence of this fading coefficient h in the wireless communication system. We earlier saw that this h can be represented as a e power j phi, where a is the magnitude, it is Rayleigh distributed, a is the Rayleigh distributed magnitude, and phi is the phase which is uniformly distributed in minus pi on pi, minus pi and pi. For the purpose of the bit error rate analysis, however, we will need only information of the magnitude, because it depends, the gain depends only on the magnitude. We will not need information about the phase factor phi. All right. So, in a wireless, let us say the power in the signal is P, that is the power in signal, the power of the signal is similar as earlier, equals P. Remember, we want to compare the performance of wired and wireless communications for the same transmit power, all right, and the noise power equals sigma n square. Let me write this as power. So, power of the signal equals P, power noise power equals sigma n square, and now remember that the channel equals is given as y equals h x plus n, all right. So, what is transmitted is multiplied by a fading coefficient and received in the presence of noise. So, the received power in a wireless communication system is simply the transmitted power P times h square, that is magnitude of h square, where h is the fading coefficient, and this we know is simply P times a square. The received power is transmit power times the gain of the channel. The gain of the channel is magnitude h square, which is simply P times a square. Remember, we said h is given as E j phi, the magnitude of h is a, hence the received power is P times a square. Hence, the received SNR is P a square divided by sigma n square. I can also write this as a square times P over sigma n square, all right. So, I am writing this received SNR as a square times P over sigma n square. Now, this is similar to the AW channel, which is similar to the wired communication channel. Remember, let us do a comparison. In wired channel, we said SNR equals P over sigma n square. In a wireless channel, SNR equals a square times P over sigma n square. Now, everything is same between wired and wireless in terms of the system model, except the SNR in the wired channel is now multiplied by a gain factor, which is a square. So, the bit error rate here we said is q times square root of P over sigma n squared, which means the SNR here will be q times square root of a squared P over sigma n squared, all right. See, the SNR from a wired to a wireless channel is essentially, the difference is this SNR P over sigma n squared is scaled by a square. Hence, if this bit error rate is q square root of P over sigma n squared, this bit error rate is q square root of a squared P over sigma n squared, and hence the bit error rate is simply, remember, we defined the q function as the cumulative distribution function of the standard Gaussian random variable. So, this bit error rate of the wireless channel is simply square root of integral square root of a square P over sigma n square to infinity 1 over square root of 2 pi e power minus x square by 2 times t of x. Alright. So, we derived an expression for the bit error rate of a wireless communication system as a function of a, which is q times square root of a square p over sigma n squared. Now, q function is the cumulative distribution function of the Gaussian random variable, standard Gaussian random variable. So, the bit error rate is simply q, which is integral square root of a square p over sigma n squared to infinity 1 over square root of 2 pi e power minus x square by 2 over e power minus x square over 2 d of x. However, observe that this a here is a random quantity. We said earlier that a, which is the gain of the Rayleigh fading channel, depends upon the random multipath components. Hence, it is a random quantity. In fact, we said this random variable has a Rayleigh distribution, which means this bit error rate is going to be a function of this random gain of the Rayleigh fading channel. Hence, to get the average performance of this Rayleigh fading channel, now I have to take this bit error rate, which is a function of this random quantity, and average it over the distribution of that random variable. Alright. For instance, for any function of a random variable. So, let us say I have function g, which is a function of the random variable a. The average of g is computed as g of a times f of a integrated between the limits. Since the limits of a are 0 to infinity, remember the amplitude has a limit from 0 to infinity. This is g of a multiplied by the probability density function f of a times d a integrated between the limits 0 to infinity. This is the average of g of a. Hence, if you look at this bit rate, I have to similarly average this over the distribution of the random fading coefficient gain a to get the average bit error rate of a wireless communication system, and that is what I am going to do next, which is I want to compute the average bit error rate of a wireless system, which is the bit error rate of a wireless equals, remember the bit error rate as a function of a is simply q times square root of a p over sigma n square. This is the g of a times f of a, which is the distribution of the fading coefficient, which as we know is 2 a e power minus a square integrated between 0 to infinity d of a. So, what am I saying? I am saying that the bit error rate of a wireless system is q of square root of a p over sigma n square, which is a function of a. I am multiplying this by the distribution of a, which is 2 a e power minus a square, and averaging this over 0 to infinity. This gives me the average bit error rate. So, this, let me write this as the average BER, which is the BER, the average BER, because remember bit error rate is not an instantaneous statistic, but it is an average quantity. That is, if you look across bits, large blocks of bits and different instantiations of the wireless channel and compute the average bit error rate, that is the correct bit error rate for this system. So, now we will do some rigorous set of rigorous mathematical manipulations to compute the average bit error rate. Remember, we want to simplify this expression further. Unfortunately, it involves some lengthy elaborate mathematics, it is a lengthy mathematical procedure, but we have to go through that procedure to derive the bit error rate of the wireless system. So, I urge you all to be attentive and slightly patient while we derive the expression of the bit error rate of the wireless communication system. So, now what I am going to start with is I am going to start with this expression, which is 0 to to infinity q of square root of a square p over sigma n square into 2a e power minus a square d of a. Remember, this is the average bit error rate. This is the bit error rate of a wireless communication system. Now, remember the Q function is nothing but the CDF of the standard Gaussian random variable. So, I am going to write the expression for that. So, this now becomes two integrals, one integral for the averaging over the A, the other integral for the CDF of the Q function, because Q function as a function of A is given as integral square root of, let me denote this p over sigma n square by the constant mu. This is a constant p over sigma n square. So, let me denote this by mu. The Q function becomes sigma integral root square root of a square mu to infinity of 1 over 2 pi square root of 2 pi e power minus x square by 2 d of x, and there is a 2 a e power minus a square d a for the outer integral into 2 a e power minus a square d a. Alright, so I am writing this as the average of the Q function over the distribution probability density function of A, which is 2 a e power minus a square, but the Q function itself is described in terms of an integral, that is, if p over sigma n squared is denoted by mu, then this Q of square root of a square mu is nothing but integral square root of a square mu to infinity 1 over 2 pi e power minus x square by 2. As you can see, this is nothing but this is the standard normal. This is the standard normal random variable. So, this is the integral, this is the cumulative distribution function, which is nothing but the integral of the standard normal variable. And now, I will make a simplifying substitution. I will substitute x by a square root of mu. Remember, square root of a square mu is a square root of mu equals u, which means dx equals a square root of mu times du. So, x by a square root of mu equals u, dx equals a square root of mu times du, which means I can write this probability, this bit error rate. So, I can write this bit error rate now as follows, that is integral, still the outer integral is 0 to infinity. However, for x I am substituting x by a square root of mu, which means the lower limit here becomes a square root of mu divided by a square root of mu, which is 1. The upper limit becomes a square root of mu or infinity divided by a square root of mu, which is infinity. Hence, this integral becomes 1 to infinity to a e power minus a square times a square root of mu times e power minus x square. Now, x as we have seen is a square root of mu times u, which means x square is a square mu u square. So, that is what I am going to write over here, which is minus mu a square u square over 2 times du times dA. Alright. So, now I have simplified the bit error rate as this double integral, which is 0 to infinity 1 to infinity 2 a e power minus a square root of mu e power minus mu a square u square by 2 du dA, and divided by there is a factor of 1 over square root of 2 pi. Now, I am going to use a trick that we often use in electrical engineering very frequently, especially in the context of Fourier transforms and other such manipulations, which is I will now flip the order of these two integrals. Remember, the first integral, the inner integral is here is with respect to u and the outer integral is with respect to a. I will flip the order of these two integrals to first integrate with respect to a and then integrate with respect to mu, and I can write this in that context as follows, which is essentially I can write this as square root of mu. The mu is a constant, so that comes out the square root of mu. I will first now flip the order of the integral. So, which means the u integral comes out, I will write that as 1 to infinity. The a integral comes in, which means I will write this as 0 to infinity, and this 2 a times a becomes 2 a square. All right. I will pull this square factor of square root of 2 pi in to write this as 2 a square over square root of 2 pi into e power minus a square over 2 times 2 plus mu u square into d a, because this is the inner integral, this is with respect to d a and this is the outer integral. So, this is the inner integral and this is the outer integral with respect to mu. So, the integral because of the flip that we did, the inner integral is now with respect to a and the outer integral with respect to mu. Now, let me first simplify this inner integral, which is integral 0 to infinity 2 a square by square root of 2 pi e power minus a square over 2 times 2 plus mu u square. Let me simplify this inner integral. Let me use the following relation for that. Let me write the relation down over here. Now, consider this integral, which is essentially 2 y square over square root of 2 pi sigma square e power minus y square by 2 sigma square between the limits 0 to infinity. So, consider this integral 0 to infinity 2 y square over square root of 2 pi sigma square e power minus y square by 2 sigma square. As you are familiar, as the audience is familiar with random processes, you will immediately recognize this as the variance of a 0 mean Gaussian random variable with parameter sigma square, and the variance of this is nothing but sigma square, right. So, integral 0 to infinity 2 y square by root 2 pi sigma square e power minus y square by 2 sigma square dy is nothing but sigma square, which means if I now multiply both sides by sigma, I will get 0 to infinity 2 y square by square root of 2 pi, because of multiplication by sigma, the square root of sigma square, which is sigma, cancels and we get e power minus y square by 2 sigma square equals, now multiplying the right hand side with sigma, I get sigma cube. So, this integral 2 y square over square root of 2 pi e power minus y square by 2 sigma square into dy is sigma cube. Now, let me write down what I had from the previous page. The integral I wanted to evaluate, the inner integral, is 0 to infinity 2 a square by square root of 2 pi into e power minus a square by 2 into 2 plus mu u square times dA. So, the inner integral that I wanted to evaluate is nothing but 0 to infinity 2 a square by square root of 2 pi e power minus a square by 2 plus mu u square into dA. Now, if you do a direct comparison, you can see that a here is equivalent to y and the sigma here 1 over sigma square equals 2 plus mu u square, which means sigma is essentially 1 over 2 plus mu u square square root, which means sigma cube is nothing but the value of this integral is sigma cube. This is equal to sigma cube, which is equal to 1 over 2 plus mu u square to the power of 3 over 2. All right. So, we said this inner integral, which we have simplified using this relation here on the right, is simply sigma cube, but sigma is nothing but 1 over 2 plus mu u square to the power of half. Hence, sigma cube is 1 over 2 plus mu u square to the power of 3 by 2, and that is the value of this inner integral. Now, going back to our original integral, I can now, this inner integral has now been evaluated. Now, I will evaluate the outer integral, and this outer integral can now be written as bit error rate equals square root of mu times 1 to infinity, integral 1 to infinity 1 over 2 plus mu u square to the power of 3 over 2 times du. So, I am writing the inner integral, outer integral now as square root of mu integral 1 to infinity 1 over 2 plus mu u square to the power of 3 by 2. Now, I will evaluate this integral and derive the final expression for the bit error rate of the wireless communication system. So, I will make another substitution now. Let me call this as t equals 2 by mu square root tan theta. I make the substitution t equals root, or let me make that substitution, sorry, not t, but rather u equals square root of 2 over mu tan theta, which means du equals square root of 2 over mu secant square theta d theta. So, I am making the substitution u equal to square root of 2 over mu tan theta, du is square root of 2 over mu secant square theta d theta, all right, which means 2 plus mu u square is nothing but 2 plus mu times 2 over mu tan square theta, which is essentially 2 into 1 plus tan square theta, which is also 2 times secant square theta. All right. So, this 2 plus mu u square is nothing but 2 times secant square theta. Also, the lower limit can be simplified as follows. When u equals 1, for the lower limit, root 2 by mu of tan theta equals 1, which means theta equals tan inverse square root of mu over 2. All right. So, theta equals tan inverse square root of mu over 2. Also, the upper limit u equals infinity, which means 2 over square root of mu tan theta equals infinity, which means theta equals tan inverse of infinity equals pi by 2. Hence, now I can simplify this integral as integral square root of mu. The lower limit becomes tan inverse square root of mu over 2, upper limit becomes pi by 2 into square root 2 over mu secant square theta d theta divided by 2 secant square theta to the power of 3 by 2. So, this integral, you can please verify, it can be written as the bit error rate becomes square root of mu integral tan inverse square root of mu over 2 2 pi by 2 1 over 2 secant square theta to the power of 3 by 2 into root 2 over mu secant square theta d theta. So, this bit error rate integral is square root of mu tan inverse square root of mu over 2 to pi by 2 1 over 2 secant square theta to the power 3 over 3 by 2 into square root 2 by mu secant square theta d theta, and this can be simplified as follows. For instance, you can see here that the square root of mu here cancels with the square root of mu in the denominator. There is a square root of 2 in the numerator and there is a 2 to the power of 3 by 2 in the denominator, which will give a factor of half. So, this integral can be simplified readily as integral tan inverse square root of mu over 2 to pi by 2 secant square theta by secant cube theta d theta, which is, let me write it down, which is secant square theta by secant cube theta d theta. Now, secant square theta by secant cube theta is nothing but 1 over secant theta, which is cos theta. So, this can be finally simplified as integral tan inverse mu over 2 to pi by 2 cosine theta d theta, and we know what cosine integral cosine theta is. Integral cosine theta is simply sin theta. So, this integral simplifies very beautifully, and this is now half sin theta between the limits tan inverse mu over 2 to pi by 2. And look at this, this integral has simplified so beautifully. We started with such a complicated expression that involves these rather bulky looking integral expressions of double integral, and the result is simply so elegant. It is half sin theta between the limits tan inverse square root of mu over 2 to pi by 2. Let me remind you, mu is nothing but the SNR p over sigma n square, right. Mu is nothing but p over sigma n square. So, now this is nothing but half sine of pi by 2, which is 1, minus sine of tan inverse square root of mu over 2. All right. Now, this can be simplified as, remember, sine of theta is tan square of theta divided by 1 plus tan square of theta square root, which means sine of tan inverse square root of mu over 2 can be written as tan square of tan inverse square root of mu over 2 divided by 1 plus tan square of tan inverse square root of mu over 2 whole under root, and this is now simply, we can see tan of tan inverse is simply tan of tan inverse x is simply x. So, tan of tan inverse square root of mu over 2 is simply square root of mu over 2, the square is mu over 2. So, this is simply square root of mu over 2 divided by 1 plus mu over 2, which is also essentially mu over 2 plus mu. All right. So, the final expression after this derivation process is bit error rate of a wireless system the bit error rate of a wireless system is nothing but half times 1 minus square root of mu over 2 plus mu, which is nothing but half times 1 minus S n r divided by 2 plus S n r square root. All right. So, the bit error rate of a wireless system is half 1 minus S n r divided by 1 minus square root of S n r divided by 2 plus S n r. Let me write the performance expressions of a wired and wireline system now for comparison. Wired channel wireless channel. The channel in a wired channel equals y equals x plus n, that is y equals x plus n. The bit error rate is q times square root of S n r, and a wireless channel is y equals h x plus n, and the bit error rate equals half 1 minus square root of S n r over 2 plus S n r. This is what we have derived so far. Now, let me simplify this bit error rate expression further, a little further, to give you more intuitive feel for how the bit error rate of this wireless communication system behaves. So, let me simplify this expression a little further. This bit error rate is half 1 minus S n r over 2 plus S n r square root. This can also be written as half times 1 minus, I will divide this by S n r. So, that will give me 1 over square root of 1 plus 2 over S n r, which is also half. Now, for high S n r, 2 over S n r is a small value, and we know that 1 over square root of 1 plus x for small x is approximately 1 minus half x. So, this is nothing but 1 minus half into 2 over S n r. This is, sorry, I have to write an approximate sign here. This is approximately equal to half into 1 minus half into 2 over S n r, and that is simply equal to 1 over 2 S n r. So, the bit error rate of a wireless channel, now we have a great formula for the bit error rate of a wireless channel. Bit error rate of a wireless channel at high S n r is simply 1 over 2 S n r. So, the bit error rate is approximately 1 over 2 S n r. Now, let us, to compare the performance of the wired and wireline communication systems, let us repeat the examples for the wired communication systems in the context of wireless communication system. One of the examples we did was to compute, for instance, we compute the probability of bit error rate at, let us say, a certain S n r. So, now let us start with example 1 for wireless communication system. for a wireless communication system. The problem is as follows: compute the bit error rate of a wireless communication system at SNR equals 20 dB. So, what are we trying to do? We are trying to compute the bit error rate of a wireless communication system at an SNR of 20 dB. Now, remember SNR in dB is 10 log 10 of SNR. So, 20 dB, let us compute the SNR value corresponding to 20 dB. So, 20 dB equals 10 log 10 of SNR, which means SNR log 10 of SNR equals 2, which means SNR equals 10 square, which is 100. Only 20 dB in dB SNR corresponds to 10 square, which is equal to 100. And the probability of bit error, as we saw, is the bit error rate for a wireless channel is simply 1 over 2 SNR, and the SNR value is 100. So, this bit error rate is 1 over 2 times 100, which is equal to 0.5 into 10 power minus 3. So, now we have computed the bit error rate in a wireless system, bit error rate of wireless. Let me specify this clearly: bit error rate of wireless at SNR of 100 or 20 dB, and that probability of bit error rate is 0.5 into 10 power minus 3. Now, compare this with that of a wireline communication system. Compare with wired or wireline communication system. Remember, at SNR of 10 dB, the bit error rate in a wired communication system was 7.8 into 10 power minus 4. So, the bit error rate of a wired communication system at SNR equals 10 dB was 7.8 into 10 power minus 4. Alright. Now, compare that with the performance of a wireless communication system at SNR 20 dB, which is 10 dB higher than 10 dB, which means it is 10 times the SNR of a wired system. The probability of bit error is only 0.5 into 10 power minus 3, or 0.5 into 10 power minus 3 is also 5 into 10 power minus 4. So, I am using 10 times more power than a wired communication system, but my bit error rate is still higher compared to that of a wired or a wireline communication system, and that is precisely the problem with a wireless communication system. Wireless communication system has very high bit error rate. We said, let me repeat that again. For 10 dB SNR in a wired system, the bit error rate is 7.8 in 10 power minus 4. In a wireless communication system, for 20 dB SNR, which is 10 dB more than that of the wireline system, that is 10 times the SNR of the wired system, my bit error rate is 5 into 10 power minus 4, which is still which is not larger, but which is comparable to the bit error rate of a wireline communication system. So, I am using 10 times the higher power, but I am still getting approximately the same BER, which means a wireless communication system has a very high bit error rate, and that is precisely because of the multipath interference nature of the wireless communication system that results in destructive interference at the receiver, which causes very poor signal reception. That is why the bit error rate goes higher. All right. So, let me give you now an even more precise example. Let us try to compute the SNR required to achieve a bit error rate of 10 power minus 6, which is more or less a kind of standard figure in communication systems. So, let us do example 2, which is essentially to compute the SNR required for a bit error rate of 10 power minus 6 in a wireless communication system. Remember, in a wired communication system, that SNR is 13.6 dB. Similarly, we want to compute the SNR in a wireless communication system for a bit error rate of 10 power minus 6. So, the problem is as follows: compute SNR of and SNR in dB of a wireless communication system for a probability of bit error equal to 10 power minus 6. What is the SNR required in a wireless communication system for a bit error rate of 10 power minus 6? We know that bit error rate in a wireless communication system is given as 1 over 2 SNR. Hence, this for a bit error 10 power minus 6 corresponds to 1 over 2 times SNR, which means SNR is 1 over 2 times 10 power minus 6, which means SNR is 1 over 2 times 10 power minus 6, which is essentially what is this? This value is 1 over 2 10 power 6 10 power plus 6 divided by 2. So, the SNR in dB is 10 log 10 of this value. SNR dB is 10 log 10 of 10 power 6 over 2, which is equal to, now this is equal to, remember the logarithm of fraction is the difference of the log. So, this is 10 log 10 10 power 6 minus 10 log 10 of 2. 10 log 10 of 10 power 6 is nothing but 60. So, this is 60 dB minus 3 dB. 10 log 10 of 2 is 3 dB, that is 60 dB minus 3 dB equals 57 dB. So, look at what we have achieved so far. We computed the bit error rate required to achieve a probability of bit error 10 power minus 6 in a wired communication system, that was 13.6 dB. The SNR required to achieve a bit error rate of 10 power minus 6 in a wireless communication system is 57 dB. That is, the difference is 57 minus approximately that difference between a wireless and wired communication system is 57 minus 13.6 dB, that is approximately 43 dB. I need 43 dB more power in a wireless communication system to achieve the bit error rate of 10 power minus 6. All right. So, it means a wireless communication system has high bit error rate, system has high bit error rate and poor performance, and this is because of the destructive interference or fading. This is because of fading. All right. So, let me stop here. With this, we conclude this lecture on the performance analysis of wireless communication system. I will take this forward in the next lecture and give you a more precise comparison, so that we can compare them better. Thank you very much.